Hi, I'm Craig Jibben.
I'm VanDerWolde.
And I'm Katelyn Hillson.
Our project was to develop a CPR simulator and was sponsored by Dr. Meserly.
The motivation for our project comes from the fact that there are very few anatomical heart models that exist capable of demonstrating the physiological processes occurring throughout the body. When a person practices CPR, they need to apply over 100 pounds of force to the heart at a rate of 100 to 120 compressions per minute in order to compress the chest approximately 2 to 2.4 inches. So for our project, we decided to develop a CPR simulator that's composed of a heart with 4 transparent chambers and 2 sets of unidirectional valves, a rib cage that provides the resistance necessary to simulate CPR, and then a feedback mechanism that provides feedback of the rate and depth of the compressions administered to the simulator.
The heart chambers are made out of strong, flexible, and transparent silicone. To produce these, we made a mold which can be seen in picture A. The mold itself was printed using a standard PLA filament, and the insert inside was a dissolvable PVA filament. Along the bottom you can see the more than 9 iterations we went through, with the final one being on the right hand side labeled C. To produce these, we injected the silicone into the mold using a large syringe. This was then placed in a vacuum chamber and put on a shaker plate to remove the bubbles. After the silicone was fully cured, it was placed in a warm water bath to dissolve the PVA. The external part of the one-way valves was made out of clear acrylic rod. On the inside there was a stainless steel ball and stainless steel spring. The acrylic was mainly machined on a lathe, which you can see in the top right-hand corner, and once all the components were ready, they were assembled and glued together to create a tight seal.
So for our rib cage, we used POM plastic, a flat steel bar, and some wood to construct a mold for our rib cage. How we did this was first we constructed a 3D model of it in SolidWorks. We then sent that flat pattern and the plastic to go get water jet cut. Once that was done, we assembled the wood into our mold and then heated the plastic up over that mold and bent it into the correct form. And then we added the flat steel bar underneath the sternum to add additional support to our rib cage.
Finite element analysis was performed on the rib cage to estimate stress levels as well as force required. From there, Hooke's law was used to determine the stiffness of springs that would be needed, and then after that, compression tests were completed to analyze the actual force needed. Our product will provide feedback for both rate and depth of compressions, which are both key factors when performing CPR. This will be given numerically via an LCD screen. Visual feedback will be given by multicolor LEDs, and auditory feedback will be given by a buzzer.
The final prototype includes a transparent heart composed of 4 chambers with 2 sets of unidirectional valves, which allows the user to see the fluid flowing throughout the model. The rib cage provides the resistance necessary to simulate the force required to administer the life-saving compressions, and we also have a feedback mechanism which provides visual and auditory feedback of force and depth of compressions and is also data logged. And then you can see the overall assembly of the model in the lower right-hand corner, which also includes 2 reservoirs which the fluid flows throughout. The FEA results showed that the stress levels were within an acceptable range, and then the compression test performed on the rib cage showed that about 150 pounds is required to compress the rib cage by 2 inches, as seen in the graph on the lower left. In conclusion, the visual CPR simulator was developed, which demonstrates the heart's one-way blood flow and incorporates complex feedback of rate and depth. A few more components are still required in order to assemble the final product, which were not feasible this semester due to COVID-19 complications. However, individual subtesting of components provided validity for the solution and will be able to be easily completed and assembled once complications are resolved.